Welcome to Module 1, how NetApp storage systems work. In this module we're going to talk about how a NetApp storage system works differently than other storage systems. In particular, there is the WAFL Filesystem, the Write Anywhere file layout system, that in combination with the way that a filer caches its information and the way that it uses RAID to store the information on disks makes filers, NetApp storage systems, unique solutions from all other storage systems. So in this module, we're going to cover three sections. The WAFL file system, how caching and NVRAM are used, and how disks and RAID levels are used. Section 1, the WAFL file system. In order to understand how the WAFL file system works, we're going to discuss how traditional file systems work, traditional file systems that try to avoid fragmentation, and how the WAFL file system works in contrast to that. Now, the WAFL file system was designed to allow fragmentation, a certain amount of fragmentation to take place, and this actually allows the WAFL file system to take advantage out of allowing that fragmentation to take place. In a traditional file system, every file is represented inside the file system by a file header or an iNode. Some systems call it a file header, like Windows for instance. Other systems call it an iNode, like Unix-based systems. But essentially it's the same concept. The idea of the file headers and the iNodes is that they keep the meta information, the information about the data in the file itself, where the file lives on the disk. A file header or an iNode in a traditional file system holds a number of pointers to individual extents, contiguous pieces of data on the disk. If the file is contiguous, is in one piece, the file header has only one extent. When the file gets fragmented, then it'll have multiple retrieval pointers to each individual extent. Many of the traditional file systems try to avoid fragmentation. They avoid fragmentation by, when you create a file, not putting the next file right behind it, but leaving some space there. Using bands, a concept called bands, which allows them to store files in individual bands, which leaves some space at the end of an individual file. This way, if a file needs to be extended, if a file grows a little bit in size, there is room for a file to grow. Whereas if a file would have another file stored right at the end of it, there would be no way to grow the file. You have to create a second extent where there is room on the disk. And thus, when you modify a file, the file becomes fragmented. Now, in order to understand why WAFL is so different, is made the way it is made, you have to understand what the problem is with fragmentation. There are a lot of people who say that the problem with fragmentation is that you get extra head movements. Personally, I don't agree with that view. First of all, even if we have a contiguous file, if we have a file in one piece, we will always have situations where if you go and you read or you write a piece of that file in one I/O, and then you don't do the next I/O for the next piece, contiguous piece, right immediately after that, the disk won't stop. And also you won't be alone on the system. What do I mean with those two things? Well, when I say the disk won't stop, you have a read-write head and your disk rotates at a very high speed. And so if you have a piece of contiguous data and you read or write only a part of that information, if you then don't access the next part of the information immediately, it'll have passed by your head and you'll have to wait for one full rotation of the disk for that information to become available to you again. Now, even if you have a very high-speed modern disk, like the disk that we would use in a filer would have 15,000 RPMs, revolutions per minute. 15,000 RPM disks does about 250, well, not about, it does exactly 250 rotations per second. So that means that if you have to wait for one whole rotation, you'll have to wait 4 milliseconds, which is, in our terms, a relatively long amount of time. So even if you don't have fragmented files, if you don't access all of the data at once, you split it up in two different pieces, getting two different pieces of I/O for one contiguous piece of information. If you don't do that immediately after each other, you will be facing some latency time. Now, even if the file is fragmented or isn't fragmented, and you have other people on the system, it's very likely that when your I/O is done, somebody else's I/O will be done next. So your head will move because somebody else is doing an I/O as well. And even if you would want to continue working with your contiguous file, you'd have to move the head back again. This concept of multi-user systems is quite common. We have that all of the time. Okay, we have large database systems, large email systems where we have hundreds or thousands of users on them at the same time, and we even have virtualization systems where we get hundreds or even thousands of virtual machines being virtualized onto one global storage system, doing everything for those users. So, in all of these cases, you will be facing head movements, even if you don't have fragmented files. There is one form of I/O that is related to performance loss and fragmented files. That's called a split I/O. A split I/O happens if you have an amount of data on your disk which was fragmented, which was stored in two different extents, and you would like to, but logically it's one piece of data, you'd like to access that piece of data, but now because it's physically separated into two extents, your single I/O that your application would want to do will have to be turned into what we call a split I/O. The system will have to create two I/Os to get the two or more individual fragments from the individual extents of your I/O. Now, when you observe a system for performance, when you see split I/Os happening, you know that you have fragmented files. This is actually sort of an emergency signal for most of the system administrators, telling them that it really is time now to defragment their file systems. The split I/Os are the signal really that we now have way too much fragmentation. Okay, so if the head movements are not the problem, okay, that are causing performance loss due to fragmentation, and split I/Os are like the glaring signal that things went really wrong and we really have to do something about our fragmentation now. What is that thing that's causing the normal performance loss before we see the split I/Os? Actually, it's something quite surprising. The problem is that the list of extents in the inode, in the file header, that say where the data is living on the disk, that whole list of extents, that list is a sequential list. So if an application needs to access a particular piece of information inside a file, let's say you have a big file and you're looking for block 4711 inside that file. Okay, your application just wants to have 4711 as the block number that it needs. Now, if that file is in one contiguous piece, let's say that it's a file of 10,000 blocks, okay, then all that system has to do is to take the starting point of that one 10,000 block extent, add 4711 to that starting point, and bingo, it's got the spot on the disk where the data resides that you're interested in. Now, when this file is not in one extent, when it's fragmented, what it will have to do is it'll have to take each and every single extent inside that file and find out whether the information that the system is looking for is actually inside that extent or whether it has to go on and search for another extent coming later that holds that information. Let's say you still have the 10,000 block 10,000 block file, but it's not one extent now, it's many extents, maybe hundreds, maybe you even have multiple file headers because you have so many extents that you couldn't fit them all into one file header. Okay, so the file headers are again sequentially linked. The first file header says, I have too many extents, this is the next file header, and the next one says, I'm full too, this is the next one. So what the system will have to do is, it says, okay, I'm looking for block 4711. It fetches the first extent. It finds that its extent has, let's say, 500 blocks. And it says, well, 500 blocks is not enough to cover my 4711 blocks, so it's not in the first extent. I'll have to search in the next extents to find it. But now I'm not looking for block 4711 from here on, because I've skipped 500 blocks. So I'm going to look for with an offset of 4211 now. Okay, and if the next extent has, say, 1,000 blocks, then it's not not bingo, we don't have the data, we haven't found the data there. Now we have to take the 4,211 minus 1,000 because that extent had 1,000 blocks in it. And we're looking at an offset of 3,211. And it'll have to sequentially walk all of the extents until it finally hits an extent that is larger than the remaining offset that he's looking for. And then all he has to do to find the data is to take that starting block of that extent, add the remaining offset to it, and that's where the data is living on the disk. It is this sequential process that happens every time when you try to access a block of information on the disk in a fragmented file. Some of that can be cached, but it's this process that actually makes your fragmented file system slower. The WAFL file system works very, very different from a traditional file system. It uses the same concept of iNodes. We just call them iNodes. We never talk about file headers there. So the things are called iNodes. And the iNodes are exactly the size of one block in the WAFL file system. A block in WAFL is 4K, 4 kilobytes, or 4,096 bytes. And most of that 4K is actually used by fixed-sized information that you find in the meta information of a file. So most of the information in the 4K block will consist of things like the name of the file, the date and time the file was created, last modified, last read, the access control list, so information about who is allowed to do what with that file, that sort of information. There were only 64 bytes at the end of the inode that are left available for retrieving information about that file, the actual data of that file. Now, we have a number of different possibilities of iNodes. We call them levels. In a level 0 inode, which is used for very small files, we will actually store the data itself inside that 64 bytes in the file header. So the file header, the 4K file header, and the data itself are actually stored in the same physical location. Now, obviously, you can only store up to 64 bytes into that because that's all the space you have, but there are quite a few files that are smaller than 64 bytes. Think of like an empty directory or a small text file, or even a directory with a few files in it. It may still not need more than 64 bytes to store that information. And it's very efficient because you would always have to store an inode. And then, if you would always have pointers, you would always have another block with a pointer to it that would hold the actual information. So by storing the information inside the file header itself, inside the inode itself, in a level 0 inode, is actually more efficient. What happens if a file needs to store more than 64 bytes? After all, there are many, many files that will need to store more than 64 bytes. If that happens, then we will store a level 1, 2, 3, 4 inode. Now, if we get a larger level than 0, then the 64 bytes are used as pointers. Now, instead of having a pointer to a contiguous piece of information as a traditional file system does, every pointer will point only to one block of 4K. Now, in a level 1 inode, those 64 bytes will amount up to 16 pointers of 4 bytes each, because 16 times 4 is 64. And so that allows us to address 16 individual 4K blocks, which allow us to store up to 64 kilobytes of information in the file. If the file needs to store more than 64 kilobytes, then we'll change the file header into a level 2 inode. A level 2 inode will actually have pointers to 4K blocks, but those 4K blocks won't have data in it. They'll have pointers in it to the data. So that's the difference between level 1 and level 2. In a level 1 inode, we have one pointer to the data. In a level 2, we have a pointer to the data. So we have 2 pointers to the data. Now in a level 2 inode, we have 16 4-byte pointers to 16 blocks of 4K. Every 4K block now has 1,024 pointers of 4 bytes each, 4K, to 1024 blocks of 4K of data. So we get a total of 16 times 1024 times 4K, we get a total size of 64 megabytes. If we need to store files that are larger than 64 megabytes, we can use a level 3 iNode. And of course, a level 3 iNode has 3 pointers. And a level 3 iNode allows you to go for files with a size up to 64 gigabytes. If that isn't enough, you can even go to a level 4 iNode, which will have 4 pointers to the data itself. Now, in a level 4 iNode, you will not be able to store 64 terabytes, as you might guess, because we get a 1024 multiplier for every level that we add. That doesn't work because we only have a 4-byte pointer, that's a 32-bit pointer, to address our 4 kilobyte blocks. And the 32 bits allow us to address 4 billion blocks, and 4 billion blocks of 4K each only gives us 16 terabytes. And so the maximum size that any file system, any aggregate, in fact, that's the term we use in NetApp storage system talk, can be is 16 terabytes. That's the maximum size we can get. Starting with data on tap 8, we'll have something called a 64-bit aggregate or 64-bit traditional volume, which allows us to make files and volumes and aggregates that are larger than 16 terabytes. So, but for now, we're talking about data on tap 7 here. 16 terabytes is the maximum limit, and that is what you could address with a level 4 iNode. Okay, so we have a structure in WAFL to get to the blocks, to the metadata structure, which resembles in many ways the indexes that you may find in a database. So the individual fragments, if you like, that we have in the WAFL file system are like indexed. What does that mean? If we have to get to, say, block 4711, same example I took for the traditional file system in a WAFL environment, well, actually it becomes very simple. All you have to do is you check, or all the file system has to do is, it has to check in the file header, in the iNode, to see what kind of an iNode it is. Let's say that it's, for example, a level 3 iNode. Okay? Now, if it's a level 3 iNode, it knows that there are 3 fragments of addressing. It knows that it needs to have 4 bits for the 16 pointers inside the iNode itself, followed by 10 bits that'll give the position from 0 to 1023 in the 4K block with the 1024 4-byte pointers, followed by another 10 bits. So those 24 bits in total, that's all it needs. It takes the number 4711, it converts it into a binary number, and it slices it into those 3 pieces. And every one of these pieces immediately indexes a block. And with 3 indexes, the 4th access to the disk actually gets you the data. There is no searching, there is no sequential looking for where does that data live. It's very fast and very direct. And of course, all of this stuff is excellently cached, because it's just like any other block that we access. This is really what storage systems were made to do. There is another thing that we haven't discussed yet that WAFL is perfect at, and that is supporting sparse files. There are many occasions where we don't actually need every individual block inside a file. A sparse file is a large file which only has partially data inside it. And there are big holes, typically very big holes, inside that file. Think, for instance, of a LUN. If we have a storage system in a SAN environment, we need to create something like a hard disk, which we call a logical unit number, or a LUN. And we give that LUN to a host, and the host can put its file system in there and can start working with it. Now, frequently, the host will want to have a LUN of a large size. Let's say they order with us a LUN of 500 gigabytes. But initially, they're just going to put a file system in there and a little bit of data, not much. And so maybe they're using up of the 500 gigabytes, just 2 or 3 gigabytes. Now, a filer, and NetApp storage system, will always create sparse files for all of the LUNs. So if it's only going to use up a few gigabytes, it's actually only going to take up a few gigabytes on a disk as well. And if we go thin, if we do thin provisioning, we can actually save massive amounts of space thanks to sparse files. You will also find widespread use of sparse files in virtualization environments, where either a virtual hard disk of a virtual machine is stored as a sparse file, or when one of those virtualization products is going to make snapshots. So not the snapshots of the NetApp storage system, but the snapshots of the virtualization system. Those snapshots are being stored as sparse files typically as well. The filer is capable of natively supporting sparse files, and doing that in a very, very efficient way. Okay. Let's talk about caching and the NVRAM, the non-volatile RAM. In the NetApp storage system, or essentially in any storage system, all of the memory that the storage system has, with very, very little exception, all of that memory is there just for one purpose: to cache information, either as a read-ahead cache or as a form of a write cache. Now, when we want to use the cache, the memory as a cache, we have one big problem, and that is that a system memory itself is volatile. That means that if you have a system crash or a power outage, even though you may have 2 power supplies, even though you may have things like an uninterruptible power supply, a UPS, you may still face outages whereby your memory content is lost. And so inside a NetApp storage system, we have something called a non-volatile RAM, non-volatile memory, which is battery backed up. That memory will, if a system fails, will not lose whatever information was stored in there. And it will keep that information for many days, okay? Possibly even weeks if it's a new filer. It's important that if you shut down a filer, if you want to decommission a system, that you make a clean shutdown, because otherwise that NVRAM battery will kick in and it'll keep the information safe in the batteries. And your plan was to decommission that system. So, but other than that, you don't really care too much about it unless the filer says that, hey, my batteries are growing old, you have to replace them, you have to swap them for new ones. Let's talk about how NVRAM works. Normally, in a normal NetApp storage system, the NVRAM is split into 2 halves. When a client or a host writes information, that information arrives through the network in a network packet, which is stored in system memory automatically. By the way, the NetApp storage systems try to avoid copying packets in memory because that takes a lot of CPU time and a lot of latency time as well. So we avoid copying that information. We call that an MBUF, a memory buffer. So when the information comes through the network, through any network, it arrives into the memory, it's stored in an MBUF, and it stays in there. It's processed its whole life that it stays in memory. It stays in that MBUF. Okay, once it has passed through the protocol drivers and it arrives at the WAFL layer, the WAFL layer will realize that it has to write this information, and it will never write information directly to disk, never ever. 100% of everything that's written is always cached, so we get a 100% cache hit on writing. What it will do when it arrives in the WAFL layer is it'll actually do a direct memory access. It'll tell the NVRAM card to please copy that information from the MBUF into the first half of the NVRAM, okay, the first bank of the NVRAM. When it does that, okay, the other half, the other bank of the NVRAM can be used as an assurance, as a safeguard to not lose the information that's in memory that is being written out to the disk. So at the same time that clients are writing to our file system, okay, by putting that inside our memory and then DMAing it into the NVRAM, the storage system may at the same time be copying that information from the previous clients, from the previous info, out of the memory onto the disks. Now, once the NVRAM's DMA has completed, the storage system will acknowledge to the host or the client that the write has been taken place, although it hasn't been written to the disks yet. But it's now in NVRAM, and the NVRAM copy will make sure that we will not lose it. Even if we get a power outage or a system crash or something like that, the NVRAM contents will stay available. In a failover cluster, this whole process works almost the same way, but there's a slight twitch to it. In a failover cluster, the NVRAM is actually not split into 2 pieces, but into 4 pieces. Every one of the 2 heads in a failover cluster has its own 2 pieces of the NVRAM bank. And so if a client writes to one of the 2 heads in the failover cluster, it'll actually replicate that information to his partner and put it in his quarter on the bank on the partner side, so that if a total head dies and the other head will have to take over in the failover cluster, it'll actually know what information was inside the NVRAM of the partner that died, that was already acknowledged to the clients, to the host, but hasn't been written to the disk yet. This allows the surviving partner to write that information off to the disk, and it will therefore guarantee to our clients that they will never lose any information. Once the bank in the NVRAM is full, or if the storage system wants to create a snapshot, or there are a couple of other occasions that require the information that's in the system memory to be written out to the disk, and the information is actually read from the system memory, not from the NVRAM. The NVRAM is just an insurance that we won't lose that information. The only occasion actually where the NVRAM itself is actually read is when a storage system boots, okay, and it finds that there is still data in the NVRAM, then it says, oops, I missed some information, I should have written that out to the disk, I have a dirty NVRAM, let's write it out. And of course there are some situations there where, because it did a failover to a partner, it doesn't have to write that out. So, but it'll take care of all of that. But let's talk about the concept of writing that information that is in the NVRAM from the system memory onto the disk. So we actually read the information from the system memory. The information in the system memory is rearranged, it's reordered. It's ordered in a large rectangle. We call that rectangle a Tetris. And of course it's called Tetris because of the game Tetris. Now, the purpose of the game Tetris is to have falling blocks that you have to rotate and shift in order to make full, solid stripes. We call that stripes, okay, which in the game then disappear. Now, when a storage system, a NetApp storage system creates a Tetris, what it does is it reorders the data by taking everything that comes from the same application for the same file and putting that next to each other. And it puts it in one vertical, we call that a chain. That chain will ultimately end up on one disk, okay? And of course, if there is more data than can fit on one in one chain, it'll flow over to the next disk and the chain will become bigger. And the whole rectangle will stripe over all of the disks that are available to write the Tetris to. One great thing about Tetris is that because of the reordering of the data ends on a disk in the order of one bucket of information that was written at one point in time. Now, if you don't have that, and most of the traditional storage systems don't have that, they have a lot of problems if they try to read ahead. Read ahead is a form of caching where if a client or a host requests some information and the information is not found in the system memory of a storage system, the storage system will have to go out to the disk and fetch that information, but instead of just fetching that information, it may actually fetch more information. Now, in some cases, the information that's requested is fetched plus other information that comes ascending after it. Sometimes, however, you may have a storage system that detects that a host or a client is actually working in reverse order through a file, and it'll actually take the preceding information. It'll take the information requested and the information that's preceding. And in other cases, the storage system will detect that a host or a client is actually doing random I/O, and there is no need. There is no use for getting more information that is actually requested. This is very complicated. In a filer, in a NetApp storage system, we don't typically have to make that much decisions about what to fetch. Why? Well, because all of the information that was written in one particular time frame, and the time frames is when the Tetrises are being written off to disk, which happens, by the way, in the longest interval every 10 seconds. So it'll happen every 10 seconds or shorter. So within a time frame of 10 seconds or less, we had these changes. They were squeezed into a Tetris, written off to the disk. And if now we have to read ahead, we have to go to the disk and fetch that information, and we want to read ahead, all we do is we simply read in the whole chain. Okay? That way we automatically get all of the data that was written in one piece, in one container of time off to the disk, bring it back into memory. This will automatically already give us a very high cache hit rate, a very high likelihood of the application requiring that data as well. Because most applications, if they write some random amount of information off to a disk, then they will typically, when they require one piece of that information later, they'll require the other piece as well. Think of things like a database system that has to maintain indexes. And if it ever starts searching that index, it'll presumably be interested in the data it wrote with the index as well. Or think of somebody editing a file. That whole file was written off. At one point in time, he saved it. Now he wants to load that back in again. Even though he's only asking for the first couple of blocks, we'll give him the whole file. There is one exception, though, to this rule. Sometimes we have applications that have different patterns of reading and writing. So sometimes we have an application that reads like this, but it writes like that. Okay? And that, of course, will inherently break this mechanism, because the reading ahead of the other information in the same chain will give the same information, or the information that was written in the same time frame, and not in the locality that is needed for reading. And even this is something where a NetApp storage system has a solution for. You can specify on a per volume basis. It's an advanced setting, but you can specify something called reallocate on read, which allows you to tell the filer that if it finds that, oops, I'm having read ahead misses all of the time, okay, and I have to go physically get that information from the disk, with the next time he writes out a Tetris, which is called consistency point, the next time he writes out a Tetris, to take that information that was read and put it back into a chain again in the same order that it was read before, so that in the future, if the application behaves the same way again and it reads in this order, it will get cache hits. And this allows us to get very high cache hit rates. We always have 100% cache write hits because we never write directly to a disk. Okay, and we're used to having 90% or higher, 95 or even more hit rate on a read-ahead cache, which gives us excellent performance. Every time that the NVRAM is full and we swap the two NVRAM banks and start writing the contents from the memory off to the disk, that process is called a consistency point. A consistency point, in a way, is the only point in time where the file system on the disk is actually written to. All of the other time, the file system on the disk is not written to. It's only being read if we don't get the information requested out of our cache. So what this means is that when the Tetris is built up, we build up inside the Tetris not just the change data, but also all of the metadata changes, all of the changes to iNodes and pointers and directory entries and anything that we have. The storage system will never ever modify a block. It'll always write in a Tetris new blocks into empty, unused blocks on disks. The last block in the Tetris, if you like, if you have that rectangle of the Tetris, the last block in that Tetris will actually hold what's called the root inode, which is, once that's written to the disk, that is the new root of our file system, of the entire tree, with all of the files and directories, all of the files and folders that we have in our file system. When a consistency point is halfway through, and then we get a system crash or a power outage or something like that, the old root inode is still in force, meaning that all we did when we were writing out the new Tetris out to the disk in that consistency point was we were writing some data in unused, in free blocks, and the data itself is still found in the NVRAM, and the file system on the disk is still consistent. So we never have an issue like you may have on other systems, where if you jerk out a disk while people are working with it, you have to check the disk, or file system check the disk, or something like that. You have to fix that disk again. That will never happen with the WAFL file system, with the sole exception of bugs in the software, which may cause such inconsistencies in file systems as well. So I don't want to say that we will never have inconsistent file system, but not because of a failure in being able to complete a write operation. So this makes the writes atomic writes. Everything is written there, or nothing is written. Another thing was then conceived, and that is, because we write a new root inode, what if we wouldn't just free the other blocks, the blocks that were active before, including the old root inode? What if we would just hold on to those? Then we would actually have the state of our data how it was in the past. And that is precisely the mechanism that is used to create a snapshot. If you create a snapshot on a NetApp storage system, all you actually do is you create a consistency point. So you create a Tetris, you write it out to the disk, but that root inode you write out to the disk as part of creating your snapshot, that will not be freed when the next consistency point is written out. That is actually held on to. And anything that it addresses in that whole tree, okay, that comes underneath the root inode, anything that comes after that will also be held on to. And so this actually creates a consistency point, creates a snapshot, which is a read-only version of your file system at a particular point in time. Now this, of course, is great because this means that we don't have to do something extra in order to make a snapshot. In fact, after creating a snapshot, we don't have to do something that we otherwise would have to do. Otherwise, we would have to free those blocks after creating a new consistency point. Now, when we've created a snapshot, we don't have to free those blocks because we want to hold on to them. In this section, we're going to talk about RAID and disks. We're going to discuss all of the RAID levels, so you understand what RAID levels are for what are the differences between the RAID levels. We're going to discuss how WAFL uses RAID to get optimal performance. We're going to discuss a special implementation of RAID called RAID-DP, which was made by NetApp to get even higher protection. We're going to talk about how disks can fail, and how we use spare disks to be able to rebuild the content that was lost when a disk fails. And we're going to talk about bad blocks and how bad blocks can cause problems, and what we do in order to prevent data loss through to bad blocks. Essentially, a storage system has two really important things that it must always do. It must never ever lose data. And of course, it must never disclose data to people who are not authorized to do so. Well, it's the first piece that we're talking about here. We're talking about never ever losing data that is entrusted to a file system on a storage system. The RAID levels were defined by a paper from Stanford University some 30 years ago, and have only undergone in those past 30 years some minor changes. The idea of RAID, or redundant array of independent, or originally it was inexpensive, disks, means that you want to get some form of redundancy in there. Now we have a number of standard RAID levels that everybody uses, and I'd like to point out what these RAID levels are, because they play a very important role in storage systems. So we're going to discuss RAID 0, which is not really RAID, RAID 1, 3, 4, 5, and then I'll discuss with you RAID DP, which is a RAID level made by NetApp. Okay, RAID 0 is actually not really RAID by the definition of RAID being redundant, because RAID 0 is only going to stripe over multiple disks. The idea of RAID 0 is that you have a bunch of disks and you'd like to get like a big disk with a very high performance. The idea of striping over all of these disks is essentially that you get more IOs per second because you can touch multiple disks. There's a big problem with RAID 0, and that is if any one of these disks fail, you will lose all of the information in your entire stripe, because you will essentially get holes in your data, because in that one disk, in that RAID, every stripe that you have will then have a hole where the disk was failed. There is absolutely no redundancy. That's why it's not really a RAID level, RAID 0, and so it's not used frequently in storage systems. In a NetApp storage system, there is only one case where we use it, and that is if we use a NetApp storage system as a V filer, as a V series filer, as a head that sits on top of an existing storage system. So a customer has some sort of storage system, be it EMC or IBM or Hitachi or anything that is supported by a V series filer, but the customer would like to use the advanced features that a NetApp storage system can offer to him, like deduplication, thin provisioning, snapshots, replication, that sort of stuff. Then he can create LUNs from the existing storage systems, offer those to the V-Series filer, and the V-Series filer can actually take multiple of these LUNs and put them in one big RAID 0 RAID group. And that way you get more performance, more IOs, and above all, larger storage aggregates. A RAID level that is frequently used is RAID 1. In a RAID 1 RAID level, we take two or more disks, the same size, and we look at those two disks as one disk. Anytime we write to that one disk, we'll actually copy that write. We'll write the same data to every one of those disks that are being mirrored in RAID 1. Now, obviously, if a disk fails, the remaining disk will still have all of the data available. So this does give you a lot of redundancy. The big downside of RAID 1 is the loss of storage, because you effectively net out at 50% of your gross storage, or less, depending on whether you have two or more disks. In terms of performance, RAID 1 is not so good for performance. If you have to write to a RAID 1, you have to write twice, which actually will cost you a little bit of performance. If you read from a RAID 1 RAID array, then you can read from either head, and that makes it possible to do two reads at the same time, two different reads at the same time. So you may actually have a slight performance plus a performance bonus out of RAID 1. Typically, because most workloads have more reads than they have writes, you may net out in a RAID 1 environment to get a small performance bonus of maybe 20% or something like that. Although, please be aware that there are some environments like the transaction log file of a database, which is exclusively writes. You get only writes there, where you actually net out having a performance loss, not a gain. Many people will claim that it has a performance gain, but it has better performance as opposed to a RAID 5, which is a whole different thing. You can't compare these two. I won't discuss a RAID 2, but we are going to talk about RAID 3, 4, and 5. Now, all of these, RAID 3, 4, and 5, are all actually the same kind of RAID system. Their basis is exactly the same. It's striping with parity. Striping with parity means that you take a number of disks, as in RAID 0, you stripe your information over those disks, and then you have a parity that you calculate over that stripe. Now, whenever you lose one disk in that stripe, thanks to the parity, you know how to reconstruct the contents of that failed disk. This principle is used in both RAID 3, 4, and 5, but it's used in slightly different variations, and we'll talk about those details in just a second. Now, let's take one example of a stripe here. Let's say that in the data blocks I have values like 2 and 3 and 5 and 0. Then the sum of those values, the 2 and the 3, the 5 and the 0, is 10. And essentially our parity has like the value 10 in there, except that we will use an XOR, an exclusive OR operation, which will not make that sum bigger than the individual operands that we've been adding. Now, if one disk fails, let's say the disk with the value 5 fails, then you know that the remaining disks still have the 2 and the 3 and the 0, which adds up to 5. You know that the sum had to be 10, so the failed disk had to have the value of 5. That's essentially how RAID 3, 4, and 5 work. In a RAID 3 system, the IOs that you take are so big that they will always touch the entire stripe. This has advantages and disadvantages. One obvious advantage is that if you have to write to a RAID 3 array, since you are going to have all of the data for the entire stripe that you write at one time, you can easily calculate the parity in the memory of the system that is writing to the RAID 3 and just write out all of that information at once to disk. So there is virtually no overhead in calculating or updating the parity. The disadvantage is that since every disk in a stripe has a number of IOs per second that it can do, the entire aggregate, the entire RAID array with all of the disks will in RAID 3 not get a higher number of IOs per second, in spite of the fact that you have multiple disks available to you. Why? Well, because every IO will touch on all of the disks at the same time. So, in effect, the entire RAID 4 RAID group will perform with the same number of IOs per second as an individual disk does. This means that RAID 3 is used for some specialized applications typically. Applications like recording a live video stream, which gives you a massive amount of data, which would be too much for one disk to handle. And also you want to have some RAID system, you want to make sure that you don't lose whatever you're recording. And so in such situations, you'd get a continuous stream of data and you would stream that out onto a RAID, a RAID 3 stripe where all of the data would be securely saved on disk. in RAID 4. Now, a RAID 4 system, its physical layout is the same as a RAID 3. The only difference is that now the IOs are so big that it will typically touch on one disk in the entire RAID group. This means that the advantages and the disadvantages of RAID 3 are exactly the inverse. If you want to write to a disk, what used to be an advantage for RAID 3 now becomes a disadvantage, because in RAID 4, when you write to just one disk, you have to update the parity information that belongs to that stripe. The problem is that you don't know how to change that, because you have the new data to write to that block, but you don't know what the old parity is, you don't know what the old data, you don't know what the data of the other disks is. Essentially, you have two options. One option would be to read all of the remaining data disks plus your one new data and calculate the entire stripe into a new parity. This is, of course, a very, very bad solution, because this means that if you have n disks, you're actually going to, in order to write to one disk, you're going to read from n-2 disks and write to 2 disks. So you're going to do n IOs, which means that the more disks you have in a RAID group, the more overhead you're going to have as well. The other option is that you could read the old data, read the old parity, subtract, if you like, the old data from the old parity, add the new data to that subtraction, and write that new parity that you've just calculated and the new data to the disk. But of course, this also means that you have to read the old data in the old parity, and then you have to write the new data and to write the new parity. This means you're doing 4 IOs for doing one single write. That's, again, at least a 300% overhead. What's worse is that in this whole scenario, you are always going to hit the parity disk. So whatever other disk that you're going to write to, it'll cost 2 IOs on the parity disk. So we have 300% overhead, plus we have the potential of the parity disk to become a bottleneck for all of the other disks when we start writing. Now, if we go and we read from a RAID 4 RAID group, we get excellent performance, because when we read, we can read from individual disks, and we can read from those disks at the same time. So we can do multiple IOs at the same time, which means that our IOPS will go up. They'll multiply with the number of disks that we have in the RAID group. A RAID 5 RAID group is essentially the same again as a RAID 3 or RAID 4. It's the same as a RAID 4, as in the IOs are the size that they will touch just a single disk, the chunk size. But other than RAID 3 and RAID 4, a RAID 5 will distribute the parity over all of the data disks. So instead of having one disk that's dedicated for parity, in every stripe, another disk is responsible for storing the parity. This will take that bottleneck that we were talking about before in RAID 4 away from the single individual parity disk, and it'll spread it out over all of the disks. Statistically seen, there is no bottleneck anymore. We still have, though, the 300% overhead, the 300% extra work for reading old data, reading old parity, writing new data, except that now the parity disk is not that disk, but one of those disks in our stripe set. The big disadvantage, of course, of a RAID 5 array is that it's hard or impossible to add a disk to that RAID group once you've created the RAID 5 RAID group. Because that parity will be diagonally dispersed over your stripes, adding a disk would actually mean you have to reorder all of those parity locations. And that is a very hard thing to do. So most RAID 5 implementations either do not allow you to change the number of disks that you have in a RAID group, or if they do, the storage systems will take a long, long time to recalculate the parity, to position all of that data in that enlarged RAID 5 RAID group. Why does WAFL use RAID 4? Well, once the Tetris has reordered all the data, it's very simple for the RAID code in the AT ONTAP to then calculate on the stripes the parity and write out all of the data in the Tetris, including the parity, straight onto the disk. In fact, this is a way of writing like RAID 3 would do it. We call it RAID 4 because actually the IOs done by the clients or the host are so small that they will actually find themselves, thanks to the reordering inside the Tetris, on one single disk. And so if we have to do a read later on, we get a read miss because the data that we have to read is not in the cache, then when we go off the disk to fetch that data, we actually typically go to one single disk. So the reordering of the data inside the Tetris will not only allow us to write like a RAID 3 with virtually no overhead, it's just the overhead for the parity disk, as opposed to the 300% overhead that we're talking about when we were doing a RAID 4 or RAID 5. But we also get, because the data is reordered, an opportunity to actually fetch all the data that was written together in one time frame at once back again. And we already discussed that, including the reallocate on read. Alternatively to RAID 4, there is another RAID level that you can use on the data ONTAP system, on NetApp storage system. That is RAID DP, or RAID double parity. RAID DP was actually just discovered some 6 years ago in 2004 by NetApp. NetApp wasn't very happy about the existing RAID 6 implementations that other vendors are using, partly because the RAID 6 implementations that are in use by others are built upon RAID 5, which is one of the things we don't want because of the overhead that is involved with dealing with RAID 5. And we don't need that because of thanks to the way that we work with the Tetris and we reorder the data. But also, NetApp was looking for a way to get the high redundancy of the data you get from a RAID 6, from having not just one disk that holds the redundant information, but actually two disks per stripe that hold redundant information. So you can lose two disks. NetApp also found that the implementations like the even odd or datum or the Reed-Solomon codings that we were seeing for RAID 6 implementations were way too complicated. Complicated algorithms, difficult math, and so they were looking for a way that they could use the simple exclusive OR mechanisms that were used, that formed the basis for RAID 3, 4, and 5, to use that in a RAID double parity environment as well. And RAID DP does that. Now it does that by storing the second parity information as the sum of diagonal stripes of data, excluding one disk. And that's very important. The exclusion of the one disk means that if you have a failure of two disks, or what is actually more likely a failure of one disk and a bad block on another one, it allows you to actually find a diagonal stripe which has just one disk missing. After all, if you just have a horizontal parity and there are two disks or two pieces of information missing, you know what the sum is of everything. You know what the individual other components, except for the two failed one, are, but you have no clue how much of that sum of those two will actually go to what disk. Now, thanks to the diagonal stripes, the sums over the diagonal stripes that we create, RAID DP allows you to actually find one diagonal that has only one disk missing, because it leaves out one disk in its diagonal stripe creation. Using that diagonal stripe, we can then calculate the value of one missing disk, and then we can use the horizontal parity calculation to actually find out in that same stripe a second block that's missing. And that will become part of another diagonal stripe, which again allows us to then have a diagonal stripe that before had two blocks unknown to find out that one. And using a combination of horizontal and diagonal parity calculations, we can actually rebuild the entire contents of even a RAID group that has two disks missing.